10.3, the inverse of a matrix. So yesterday we talked about Gauss-Jordan elimination, and we were converting a matrix to the identity. And by doing so, that would give us the answers to a system on the right side. So now we're going to talk about inverses. What is the multiplicative inverse of the number 6? 1/6. Because 6 times 1/6 is 1. Okay. A matrix inverse is the same thing. I've got a matrix. I want to multiply this matrix by something to get the matrix version of 1. What is the matrix version of 1 called? The identity matrix. Okay. So if I can take matrix A and multiply it by matrix and get the identity, oh, by the way, we can switch it too. Or if I multiply matrix B by matrix A and get the identity, they're inverses.
So the identity matrix is the one with the 1.
All ones on the main diagonal, everything else is zeros.
And what's the one with all zeros?
A zero matrix. Or it's the additive identity, which is not the same thing as the identity matrix. Okay. A matrix of all zeros, if you add it to a matrix, you get what you started with. That's the additive identity. A matrix that you can multiply by to get the identity is called the additive inverse. It's a mess, or multiplicative inverse. Okay, we're going to use the Gauss-Jordan elimination to find the inverse of a matrix. We're going to use a formula to find the inverse of a 2x2 matrix. And then we're going to use inverse matrices to solve systems of equations. This section further develops the algebra of matrices. To begin, consider the real equation AX equals B. To solve the equation for X, okay, forget what it says right here. I've got the equation AX equals B. How do I get X by itself? AX equals B. So you're telling me if I divide both sides by A, I get that X is equal to B over A. And that's true. Okay. What is another way of making the A go away? Multiply it by what? Multiply it by 1 over A, right? And if I do that to both sides, I get X equals B over A, correct? Okay, another way to think about it. If I multiply both sides by A to the minus 1, what does A to the minus 1 mean? It means 1 over A, doesn't it? So when you multiply two things together, when the bases are the same, what do you do to the exponents? When the bases are the same, what do you do to them? What is A to the minus 1 times A? Remember this A, it's not written, but that is to the first power. When the bases are the same and you're multiplying, what do you do to the exponents? You add them. So that would be A to the minus 1 plus 1, which is A to the 0. And anything raised to the 0 power is 1. Okay. This is what we're doing. I've got AX equals B. If I multiply both sides by A, which is the inverse of A, I get those A's cancel because that's just a 1. And over here, I can't do anything with it, so I just keep it. A to the minus 1B is the exact same thing as B over A, isn't it? How do you get rid of a negative exponent? You pass it through the fraction bar, and it makes the exponent positive, right? Nothing here. It's just a new way of writing stuff. A to the minus 1 is called the multiplicative inverse of A because if you take a multiplicative inverse and multiply it by its multiplicative inverse, you're going to get 1. We're using this terminology here, because there's not really a definition to divide matrices. I can multiply matrices, but I can't divide matrices. So instead of dividing matrices, I will multiply by the inverse. Okay? So again, we're going to take this approach as we move forward in solving systems of equations involving a matrix. The definition of the multiplicative inverse of a matrix is similar. If A is an n by n matrix, and I sub n is the n by n identity matrix, if there exists a matrix A inverse such that A times A inverse equals I, which is the same thing as A inverse times A, what's the difference here on these two? They swapped, right? Okay, so again, two matrices are inverses. If you multiply them together, you get the identity, and order doesn't matter in this case, okay? Then A inverse is called the inverse of A. The symbol A inverse is read A inverse, in case you missed that. Show that B is the inverse of A. Okay, 2 by 2 matrix, 2 by 2 matrix. I want to know, are they inverses of each other? To find out, I multiply them together twice. One time I do it as A times B. The other time I do it as B times A. So let's do A times B. That would be -1, 2. I'm just writing down matrix A right now. -1, 1 times matrix B, which is 1, -2, 1, -1. And I want to know, are they inverses? How do you multiply a matrix? Row by column. Okay, Matt, pay close attention since you weren't here yesterday. The first matrix, I'm going to look at row 1. The second matrix, I'm going to look at column 1. Okay, so in row 1, column 1 of my answer, I have -1 times 1 plus 2 times 1. That's row 1, column 1. I will now do row 1, column 2. -1 times -2 plus 2 times -1. I went across the row, I went down the column, matched everything up. I'm now going to go with row 2, column 1. Row 2, column 1, that's -1 times 1 plus 1 times 1. And finally, row 2, column 2. -1 times -2 plus 1 times -1. Now let's do the math. -1 times 1 is -1. 2 times 1 is 2. -1 plus 2 is 1. -1 times -2 is +2. 2 times -1 is -2. +2, -2 give me 0. -1 times 1 is -1. 1 times 1 is 1. -1 and 1 give me 0. -1 times -2 is 2. 1 times -1 is -1. 2 and negative 1 give me 1. Is that the identity? Okay. So by checking A times B, I do in fact get the identity, but you have to go both ways. You have to do the other one. I'll let y'all screenshot that if you want to. I'm going to move on. And the next slide has the B times A worked out. I'm not going to spend time on it, okay? Just for sake of time. Good? Okay. Here's B times A. Once all that's worked out, what do we get? The identity. So I showed you that A times B was the identity. Here's B times A, it's also the identity. So because A times B equals the identity, which is the same thing as B times A, are matrix A and B inverses? Yes. Okay. So this is an example of a square matrix that has an inverse. It is possible that a matrix does not have an inverse. Does every number have an inverse? What's the multiplicative inverse of 6? 1, 6. What's the multiplicative inverse of negative 7? Negative 1/7. What is the multiplicative inverse of 25? 1/25. What is the multiplicative inverse of negative 10? Negative 1/10. What is the multiplicative inverse of 0? Because to find the multiplicative inverse, you take 1 over, right? And what's 1 over 0? Undefined. Okay, that makes sense? So that's what's going to happen here with matrices. You can't divide by 0. And it'll make more sense when we get to the formula for solving an inverse by using the formula. Make sure that was the last part of that slide, and it was. Yes, we're good. If a matrix A has an inverse, then A is called invertible or non-singular. Otherwise, A is called singular. A non-square matrix cannot have an inverse. Well, why not? What does the additive, what does the identity matrix look like? Describe it to me. It's square, right? If the identity matrix is squared, then the only way I can get an inverse is if I have a square matrix times a square matrix, right? Okay. When A is of order m by n and B is of order n by m, where m and n are not equal, the products A, B, and B, A are different. So they can't be equal to each other. No, not square matrices have inverses either. When a matrix does have an inverse, that inverse is unique. Next example is going to show us how to use a system of equations to find the inverse of a matrix. Okay, if you are following along the notes slides, they use a lot of subscripts. I'm going to work this without using subscripts, okay? I've got a matrix, and that matrix is 1, 4, -1, -3. I want to find some matrix. So I don't know the inverse. I want to find the matrix that gives me an answer of the identity. So first of all, we're going to write our matrix equation. Do you know what matrix A is? It's right there, right? Do you know what matrix X is? This matrix is going to be full of variables. It's going to have 4 variables in it. Okay, so let me show you what that looks like. Okay, matrix A, 1, 4, -1, -3. Matrix X, I don't know. I need to find out what A, B, C, and D, and R. It's possible that maybe A and D are the same, or maybe A and C are the same. But it's also possible that all 4 numbers are different. but I want this matrix times my unknown matrix to equal the identity. Yes.
So that's always going to be the identity, like 1, 0, 0, 1.
The identity will always look like this. I'm going to be very generic on the identity here. The identity is some matrix that's got ones on that diagonal. I don't know how many ones are on that diagonal. Depends on how big the matrix. Everything here are zeros. Everything here are zeros. That's the identity.
So if it has like a 2, then
It's not an identity. Now, how would you multiply this? How would you multiply matrix A times matrix X? Row times column, right? 1 times A plus 4 times C. That makes sense? And then I would go 1 times 4, 1 4 times BD, 1 times B, 4 times D. So I would have A plus 4C right here. And the next one's going to be B plus 4D. Y'all following that or no? Again, A plus 4C, B plus 4D. Second row, what are we going to do? Same thing, but different row. So -1, -3 times AC. That would be -A minus 3C and, y'all good with that? There it is. Y'all ready for me to move on talking about this? Take a look at column 1 on both of those. It's a call from the nurse. Someone check their computer, make sure my volume's still coming through, please. Turn it up for a second. Check, 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 check. Hello, hello, hello. Good, thank you. Okay, notice column 1, A plus 4C, -A minus 3C, right? Notice column 1, 1, 0. Can you see if that's a system of equations? A plus 4C equals 1. A minus 3C equals 0. Is that a system? 2 variables, 2 unknowns, 2 equations, 2 unknowns. How about column 2? B plus 4D equals 0. -B minus 3D equals 1. Is that a system? Yes. Okay. I'm moving on. Here's what we started with. I just talked through the system of equations. So by looking at that information right there, I can write it as 2 separate systems of equations. Could y'all solve this one pretty easily? Right? Combine them, what happens? A's are gone. C equals 1. Pretty simple. If C equals 1, plug a 1 in right there. What's A going to be? A plus 4 equals 1. So A is -3. Right here, can we do the same thing? B's are gone. What's D? D equals 1. Plug a 1 in right there. B plus 4 equals 0. B equals -4. Now remember, A, B, C, and D happen to be elements of a matrix, right? And that's going to be the elements of our inverse. So we solved the first system using elementary row operations to determine that. And we didn't, we used elimination, but it doesn't matter. We got A to be -3, we got C equals 1. I'm about ready to move to the next slide. Okay. Doing the same thing with that second equation, we got B equals -4 and D equals 1. So here's the inverse. A was -3, B was -4, C was 1, and D was 1. And now, as usual, once you have an answer, check it, right? Take my original matrix, which was 1, 4, -1, 3, multiply it by what I claim to be the inverse, and identity. In this case, yes, I do. If I swap them, I will also get the identity. And here's the check going the other way. We get the identity. Okay. How are we doing, guys? Matt, how you doing? Are you okay? Not really. Well, missing yesterday was, yeah. Okay, good. So in example 2, note that the two systems of linear equations have the same coefficient matrix. Rather than solve the two systems represented by 1, 4, 1, -1, -3, 0, and 1, 4, 0, -1, -3, 1. Separately, it's the next line, next word. You can solve them simultaneously. Okay, so this is another way of finding the inverse. If I want to find the inverse of A, what I can do is make one matrix of the matrix I'm working with joined with the identity. And if I perform row operations on these to make, if I can turn A into the identity, the right side is going to be the inverse. Okay. So let's do that. I have the matrix 1, 4, 1, 0, -1, -3, 0, 1. I want to make the left side. Well, my first number is already a 1, so I'm happy with that. So step number 1, I'm going to leave row 1 alone. 1, 4, 1, 0. What can we do with these two rows to turn the -1 into a 0? Yeah, if I want this to be the identity, I got to make that -1 go away. That's it. I'm going to take row 1 plus row 2. I'm now going to have a brand new row 2, right? So when I combine these, 1 and -1, 0. 4 and -3, 1. 1 and 0, 0 and 1. I'm trying to make this left side the identity.
Wait, it's your, you have to. You have to.
Correct.
Oh, wait, no, no.
It was the identity, but as we do row operations, it's going to change. Okay. Now, pay attention. This is very important on your homework. This is now row 2. So if I go to my next step on this problem, this is row 2. This is not row 2 anymore. Okay. I had several people asking about that during college lab today, not just one. So I have a 0 here, but that 4, I need to get rid of that 4. How? Okay, so I'm going to take -4 times row 2. I wrote that in the wrong spot. 1 second. Because that's going on the top, right? Okay, so I'm going to take -4 row 2 and add it to row 1. Is my row 2 going to change right now?
No.
This row is going to stay the same. So I'm going to go write it down. 0, 1, 1, 1. Okay. Since I am multiplying this row by -4, I always actually do the math up here. -4 times 0 is 0. -4 times 1 is -4. -4 times 1 is -4. -1 times 4. Okay, it's still -4. Now let's combine those. 1 and 0 is 1. 4 and -4 is 0. 1 and -4, -3. 0 and -4, -4. My left side is now the identity. My right side changed. This right side is the inverse to 1, 4, -1, -3. Isn't that what we got a while ago? It's the same problem, isn't it? A was -3, B was -4, C was 1, D was 1. Okay. So this is just another way. So what we did was we used elementary row operations. Again, if you're following the notes on the handouts, this sentence wasn't there. I wrote that in this morning. Use elementary row operations to turn the left side into the identity. If I'm turning the left side into the identity, the right side becomes the inverse of the original equation, of the original matrix. Any questions about what just happened? Because when I took -4 row 2s, that's this red part, and added it to row 1, 1 plus -4 is -3, 0 plus -4 is -4. Other questions? I don't know. Will Smith will find him and slap him though. It's all good. So from the doubly augmented matrix AI, you obtain the matrix IA inverse. And that's what we just did. This procedure works for any square matrix if it has an inverse. And I don't know about you, but I think this was better than the whole ABCD situation when then we had to solve a system. Right? So, all right. So finding an inverse of a matrix, let A be a square matrix of order n by n. Write the n by 2n matrix that consists of the given matrix A on the left and the n by n identity matrix on the right. If possible, row reduce A to I using elementary row operations on the entire matrix. The result will be the matrix IA inverse. If this is not possible, then A is not invertible. You will run across situations where you will not be able to get the identity on the left side. If that happens, that tells you that that matrix has no inverse. Check your work, multiply them together, see if you get the inverse the identity both ways. Using Gauss-Jordan elimination to find the inverse of a matrix works well, even if we're talking about matrices greater than 3 by 3. However, 2 by 2 matrices, some people prefer to use a formula, and I'm about to show you that formula on how to find the inverse of a 2 by 2 matrix by doing an inverse or by doing a formula. And it's not that bad. I've got some matrix, ABCD. I want to find the inverse of that matrix. The first thing I have to do is calculate the determinant. We'll talk about that in just a second. AB is the down diagonal. If I multiply A times D, and I multiply B times C, if those two numbers are equal, there's no inverse. If the cross products are equal, then there is no inverse. I can just, okay. To find the inverse, it's 1 over down minus up. Then we started with A, B, C, D. And this is how I've said this for years, and some kids figure it out. I'm going to rearrange this. First thing I'm going to do is swap the DNA. Swap your DNA. Change signs under B and C. Swap your DNA. Change signs under B and C every time. That's the formula. Okay? Letter A. Let's find the inverse using the formula. A inverse equals. First thing I want to do is calculate the determinant. The determinant. That would be 3 times 2, the down diagonal, minus the up diagonal, -2 times -1. What is 3 times 2 minus -2 times -1? So it's not 0. Okay, so because it's a 4, I can proceed. So the inverse is going to be equal to 1 over that determinant times, swap the DNA. So the 3 and 2 change positions. So the 2 comes up here, the 3 goes down here. Change signs on B and C. So -1 becomes +1, -2 becomes +2. Multiply everything by this scalar. What is 2 times 1/4? 2 times 1/4? 1/2. 1/4 times 1? 1/4 times 2? That's a 4. That's clearly a 4. 1/4 times 2? 1/2. 1/4 times 3? That's the inverse.
Where did you get the 1/4?
To calculate the inverse, it's going to be 1 over AD minus BC. AD minus BC is called the determinant. We took the down diagonal. So I did the determinant first. I took the down diagonal, 3 times 2, minus the up diagonal, and got 4. So it's 1 over the determinant, 1 over 4. Any other questions about that one? Okay. There's the determinant is 4. Multiplying everything by 1/4. And that's what they got. Same thing we got. I'm going to go back a slide and let's do the other one. B inverse. First thing I want to do is calculate the determinant, which means the down diagonal, 3 times 2, minus the up diagonal, -6 times -1. I get a 0. Which means if I wanted to use the formula, I've got 1 over 0. Can I do that? No determinant exists. I mean, no inverse exists. Okay. That's why we always do the determinant first. Oops, let me go back to the bottom there. Just pull up their slide. So they got the same thing. So they say B is not invertible. You know that a system of linear equations can have exactly one solution, infinitely many solutions, or no solution. If the coefficient matrix A of a square system, a system that has the same number of equations as the variables, is invertible, then the system has a unique solution, which is defined as follows. Yeah, I don't want to get into this. We'll continue here tomorrow.
You be recording this tomorrow?
Yes.